Good morning everyone. Today we will start the revision for network analysis for TG Transco. Starting we'll discuss about basics, what type of elements we'll use in network analysis. Later we'll discuss about resistors, inductors and capacitors. Next we'll discuss about dependent and independent sources. Next we'll discuss about Kirchhoff law, star delta conversion. Next we'll discuss about the equivalent resistances. Further we'll discuss about the theorems. Finally we will conclude today with some beautiful problems which were asked in the competitive exams. Okay, without wasting time, now we can talk about the what are the types of network elements. We will use two types of network elements, linear and non-linear. So linear elements have both positive and negative slope common. We will take on y-axis as voltage and x-axis as current. These are linear elements. And in the non-linear elements, slopes are different in both first and third quadrant. Okay, if the slopes are same in the first and third quadrant, they are called as a linear elements. If the slopes are different in the first and third quadrant, it is called as non-linear element. Next we will talk, this is A and this is B. Next we will talk about the active elements and passive elements. In these active elements, we will take same on x-axis as I and y-axis as V. If the second quadrant and third quadrant are same, they are called as active elements. These active elements are the elements which will give out the electrical energy. In this you can give examples as BJT, next MOSFET. Passive elements, in this, if first and third quadrants, so first here, first, second and fourth, here first and third quadrants are same, they are called as passive elements. These are passive elements are the elements that observe, dissipate or waste or convert electrical energy. Those are called as passive elements. In these examples are resistor, inductor and capacitor. So here is a note point: all active elements are non-reciprocal in nature. This is the question asked in one of the competitive exam. Or if any element having amplification property, they are also called as active elements. Okay. See, examples for linear elements are resistor, inductor and capacitor. Examples of these non-linear elements are diodes. Okay, next we will talk about unilateral and bilateral elements. Unilateral and bilateral elements. Okay, Same, if first quadrant is equals to the third quadrant, then they are called as bilateral element. Or if second quadrant slope and fourth quadrant slope are same, they are called as bilateral elements. If first quadrant is not is equals to third quadrant, they are not called as unilateral elements. And if second quadrant is not is equals to fourth quadrant, they are called as unilateral elements. So finally we have talked about the three terms: linear and non-linear, active and passive, unilateral and bilateral. Now we will talk about the components of electrical networks. First we will discuss about the resistor. Resistor which opposes the flow of current. We will represent this resistor by R, which is equals to rho L by A. Here L represent length of a conductor and A represent area of cross section. Okay, this resistor will follow Ohm's law, which is V of t is equals to I of t into R, where V is voltage and I is current and R is resistance. Here V and I are linearly related at constant temperature. So Ohm's law we can represent in Laplace transform as V of S is equals to I of S into R. Same Ohm's law we can represent in Fourier transform as V of omega is equals to I of omega into R. Ohm's law in point form we can say as J is equals to sigma E, which is the standard formula, where sigma is known as conductivity. Standard resistor must have high electric resistivity and must be high, and temperature coefficient must be low. Average power in resistor can be represented as IRMS square into R. This average power is suitable for periodic voltage and current. Next we will talk about the electric power, which can be represented as rate of change of work with respect to charge into rate of change of charge with respect to time. When these two elements, power can be represented as rate of change of work with respect to time. This is an important formula. Next we will talk about electrical energy. So we will represent it as W. Energy is nothing but integration of power with respect to time. Here P of t is constant. Work is also can be represented as power into time. Now we will talk about the second element, that is inductor. Inductor is an element which does not allow sudden change in current. So the units of inductors are Henry or voltage second per ampere. Here voltage across the inductor can be represented as V is equals to L into di by dt, where di by dt is nothing but rate of change of current with respect to time. The formula for the inductor is L is equals to mu n square A divided by L. This is the standard formula for an inductor. Here positive sign represent if current enters the positive terminal, and negative sign represents if current leaves the positive terminal. Laplace transform for this voltage is V of s is equals to SL into I of s, and next Fourier transform is V of omega is equals to J omega L into I of omega. So electric power in inductor can be represented as P is equals to V of t into I of t, where V is equals to L into di of t by dt into I of t. This can also be written as L into I of t into d by dt of I of t. Energy, which can be represented as W. Here you can use the formula half L into I of t whole square. This is the energy stored at time t. So don't waste your time by integrating power in while calculating the energy in an inductor. Rather use this formula so that you will save this time. I will discuss one problem related to this topic. Now note, ideal inductor has resistance as 0, and this is practical resistor, which is represented with small internal resistance which has low value. Now we will discuss about the another electrical component, that is capacitor. Its units are farads or ampere seconds per volts. Capacitor does not allow sudden change in voltage. This is the basic property of a capacitor. In capacitor, current is represented as I is equals to C into dV by dt. Same in Laplace transform, we can represent it as I of s is equals to SC into V of s. Same in Fourier transformer, I of omega is equals to j omega into C into V of j omega. Power in a capacitor is represented as P of t is equals to V of t into I of t, where V is equals to we can we can v, I of t is equals to C into dV by dt into V of t. This can be written as C into V of t into dV by dt. Energy, which can be represented as W. Here we can represent energy as half C into V of t whole square. Note: ideal capacitor is represented by open circuit which have an infinite resistance, whereas practical capacitor is represented with a resistance in parallel with a capacitor where resistance R is of where R is the resistance and C is the capacitor. Now we have discussed about the linear, non-linear, active, passive, unilateral, bilateral. We have discussed about the resistor, inductor and capacitor. Here I have forgot to mention that note: all linear elements are bilateral, but all bilateral elements are not linear. Now we will discuss about the voltage sources and current sources. Voltage source, these are the sources which will energize a circuit. In the voltage source there are two types. There are practical voltage source and ideal voltage source. Practical voltage source is represented with this diagram with a resistance in series with the voltage source, and this is the graph which is slightly drooping characteristics of voltage. Practical voltage source has a resistance of low value in series with it, and this is the ideal voltage source which do not have any resistance and it have constant magnitude, same as unit step signal. Next we will discuss about the current sources. In the current source also we have two types: practical current source and ideal current source. Practical current source is represented with a current source having a resistance in parallel with it which is of high value, and it is also having the current drooping characteristics. Next, this is the diagram of ideal current source. An ideal current source do not have any resistance in parallel and it has current of constant magnitude. Now we will see about the two types of dependent sources: dependent voltage source and dependent current source. Here the magnitude of source depends upon some other electrical parameters inside the network. Dependent source cannot be open circuit or short circuit during analysis. It remains same. Here first one is voltage controlled voltage source. This will be used in operational amplifier designing. We will see in the analog and electronics. And here current is dependent on voltage, so it is current controlled voltage source. Now we will see about dependent current source. Here current is dependent on the current, so it is known as current controlled current source. This is example for this current controlled current source is BJT, and this is the voltage controlled current source. Ohm's law. Ohm's law, which is nothing but V is equals to IR, which is a standard equation. Here V represents the voltage, I represents the current, and R represents the resistance. Current through an element is directly proportional to the voltage drop across it. This is at V is equals to IR is suitable at constant temperature. Here we can write P is equals to V into I, where V is rate of change of energy with respect to charge, and current is rate of change of charge with respect to time. So this both will cancel out and we'll get power as rate of change of energy with respect to time. Kirchhoff laws. We will discuss two different types of Kirchhoff laws, that is Kirchhoff current law and Kirchhoff voltage law. Kirchhoff current law denotes conservation of charge. In this, number of currents entering the node is equal to the number of currents leaving the node. This Kirchhoff current law, which is applicable for linear networks, non-linear networks, bilateral, unilateral, lamped, time variant and time invariant. Next, coming to the Kirchhoff voltage law. This denotes conservation of energy. It is independent of nature of elements. The main important point which was asked in very competitive exams is that KCL and KVL are not applicable for distributed elements. Here when voltage source and current source in parallel, it behaves it as a voltage source. Here you don't ignore the current source. It also affects the whole circuit. When here current source and voltage source are in series, it behaves as a current source. In this also you don't ignore the voltage source. We will see about the voltage division rule in network analysis. See, to apply voltage division, elements must be series. That means current must be same in each and every resistor. So voltage division, if we want to find the voltage across V1, you may have to take source voltage into opposite resistance by total resistance. In the same manner, if we want to find the voltage across V2, we have to take source voltage into opposite resistance by total resistance. Same law is applicable in inductor and it is reciprocal for capacitor. Now we will see about the current division rule, which is applicable only for parallel connections. That means voltage must be same. Here you want to find out the current in R1 resistor. You have to do current division rule by I into 1 by R1 by 1 by R1 plus 1 by R2, or else you can do it as, if you want to find the current in resistance R1, source current into the opposite current resistance by total current resistance. Now we will see about the star delta conversion. If you want to convert the star into delta, follow these steps. If all resistance are equal, R star is equals to R delta by 3, or R delta is equals to 3 times R star. Same law is applicable for inductor, and it will be opposite or reciprocal to the capacitor. If the capacitor is in series, we will take the equation as like this, opposite to the inductor and capacitor. If capacitor is in parallel, we will add all the capacitors. Same condition in inductors. For series connection, we will add the all inductors, and for parallel conduction, we will add the reciprocal of the inductors. Same thing is applicable for the resistors. If if you have n resistors, now we will see about how to transfer the current source to the voltage source. If a current source is in parallel with a resistance, it can be converted into voltage source as the circuit shown in figure with a resistance R in series. Now if you want to do voltage source to current source transformation, if a voltage source is in series with a current, you can transfer it to current source by making a resistance in parallel with a current source. Now we will see about the concept of a duality. See, in this network you have a voltage source, and in series you have an resistor, inductor and capacitor. The duality of this network will be voltage source will change as a current source, and resistance in series will become as a reciprocal of resistance in parallel. Inductor will become capacitor in parallel, and capacitor will become inductor in parallel. Note the point, the magnitude must remain same if the duality concept is applied. Concept of ladder network. In ladder network we have to see the matching pattern. See, for example, in this network you have resistance R1, R2, R3, and same thing is repeating in the following network R4, R3, R4, R3. So you can represent this total unit as one equivalent resistance network as RCD, and you can write the total network equation as RAB as R1 plus R2 parallel with RCD plus R3. Now consider one conductor which is of length L, and you have a resistance of value R ohms. Now if this conductor is stretched n times, then its new value of resistance will become n square R times. This is one important concept which is asked in many competitive exams. Now we will see about the equivalent resistance of a cube. See, here in cube you have 1, 2, 3, 4, 5, 6, 7, 8 sides. Here A and B are the edges, A and C are the diagonal faces, and A and G are opposite diagonal or body diagonal sides. Here if we see about the edges, resistance of the edges of a cube, which can be directly written as 7R by 12. If we want to find out the face diagonal of a cube, resistance of a face diagonal of a cube, you can write as 3R by 4. If you want to find the resistance of a body diagonal of a cube, you can write it as a phi r by 6. Note this these formulas are applicable for resistor and inductor, and it is reciprocal for capacitor. Nodal analysis. Nodal analysis can be defined by the Kirchhoff current law plus Ohm's law. It is dependent upon the law of conservation of charge. In this nodal analysis, here is one example for the nodal analysis. Here V1 is the voltage source and V2 is the under voltage source. Here VA is the known. We can write equation as VA minus V1 by R1, VA by R2, VA minus V2 by R3. Supernode. Here V0, VD, V0 is the supernode, which is the voltage source, independent voltage source between the two nodes. That is known as a supernode. The equation can be written as shown here. Mesh analysis. Mesh analysis is nothing but the KVL plus Ohm's law. This is dependent upon the law of conservation of energy. Here, if two loops are separated by a current source, we can use super mesh. Here is an example. This is the voltage source, this is another voltage source, and this is the current source. This is one loop and this is the another loop. In between two loops there is a current source, so it is known as super mesh. Here we can write an equation as V1 is equals to I1 R1 plus I2 R2 plus V2. Here this current is entering the node, this current is entering the node, this current is leaving the node. By KCL, current number of current sources entering the node is equals to number of current sources leaving the node. From that we can get the equation as I2 minus I1, which is equals to I0. Note an important point: all meshes are loops, but all loops are not meshes. Now we'll see about the charge conservation. Charge flow is possible if there is a closed circuit or closed path. When there is a closed path, the initial voltage across a capacitor will be V0 and initial charge across a capacitor is C into V0. Here, charge decays with time exponentially. If Q is equals to Q0, net charge will be 0. If Q is equals to Qt, net charge will be also 0. If a path exists between positive and negative plates of a capacitor, then charge travels between plates and there is no need of charge conservation. That means if there is a closed path, the concept of charge conservation will be absent and it is not at all useful to apply charge conservation. The charge conservation is applicable only when there is no closed path. When charge flow, when there is a closed path, charge flow takes place and there is no use of charge conservation. When the charge flow is not possible, then charge conservation concept comes into the picture. If multiple plates are connected together, see, these plates and these plates are connected together, and if there is no closed path, then charge on such plates will be constant. Either you take, see here, net charge is 2 into 4, q is equals to cv, which is the formula for charge. Here c is 2 and v is 4. And next, here also cv, c into v, which we will get it as minus 10 coulombs. Here positive plate and negative plates are connected together, that's why we will get the negative charge. As time reaches at steady state, the capacitor becomes fully charged. When the capacitor gets fully charged, the current flow gets stops and there is no current flow in the circuit. The net charge remains same as we have seen in the previous example, that is minus 10 coulombs. And if there is no current flow, these two capacitors will become in parallel and voltage across each capacitor will be equal as they are parallel capacitors. So now if we use Q is equals to CV, here voltage is V and C is 2 into V and 3 into V, which will be equal to the net charge. So you will get the voltage which is known as a steady state voltage, that is 2 volts. This is the long procedure. If you want to know about the short trick to find the steady state voltage across a capacitor, use this concept: V1 into C1 plus V2 into C2 by addition of both the capacitors. We will see a small thing about the power concept. If current is entering into the negative terminal and leaving the positive terminal, we can conclude that power is delivery. And if current is entering to the positive element, positive terminal of the element and leaving the negative terminal of the element, we can conclude that the power is getting absorbed. Now I will say one of the problem solving tip, how to find the voltage source if you have these types of circuit by using parallelogram law. Now if you want to find out the voltage source, see, voltage across a resistance will be in series, and this is V3, and by doing sum of these you'll get V1, and this is the angle phi. Now if you want to find out the voltage source V1, there is one standard formula: V1 square is equals to sum of other two voltage squares, V2 square plus V3 square plus 2 times V2 V3 and cos of angle between them, where cos phi is the load power factor angle. Similarly, we can see another circuit which have a voltage source and a resistance R and inductor L is in series with the voltage source. If suppose if voltage source is A plus B sin omega t plus C sin 3 omega t, then by SPT, which we'll see further in further classes, superposition theorem, we can find current as A by R, which is related to resistance, and here the frequency comes into the picture. That's why B sine omega t by Z, which is nothing but under root of R square plus omega L square whole square plus C sine 3 omega t by under root R square. Here frequency is multiplied by 3, so you will get as 3 omega L square. So don't forget to see with what the frequency is getting multiplied. Now we will discuss about the different types of theorems which is used in the network analysis. First one is the Thevenin's and the Norton's theorem. Note that in case 1, all are independent sources. Voltage source is an independent source, and this is resistance, this is resistance, this all are resistance, and this current source is also independent. Now coming to the calculations of a Thevenin's voltage or Norton's current. For Thevenin's voltage, remove the load if load with an open circuit. For Norton current, remove the load and replace it with the short circuit. For example, in the previous network, if you want to find the load current in this RL. Now for Thevenin voltage, remove that voltage source and replace it open circuit and name it as VThevenin. And if you want to find the current source in that branch, replace it with a short circuit. So for calculation of Thevenin's resistance, voltage source must be short circuited and current source must be open circuited. Open the load terminals and calculate the equivalent resistance across it. See, for example, here you want to find the R Thevenin. Now short circuit this voltage source and open circuit this current source. Now find R Thevenin. You will get as, which is R1. These both are in series. R1 is parallel. This R1 is parallel with the series of this R2 and R3. Here R Thevenin is equals to the R Norton. Now coming to the case 2, you in the circuit you have at least one source as independent source. Now how to find out the Thevenin's voltage when you have a dependent source in the network? For that, replace load resistance with a voltage source, keep the dependent source as same as it is. Now V, now find the voltage by using an equation. V is equals to I into R Thevenin plus V Thevenin. From this you will get I is equals to Norton current is equals to V Thevenin by R Thevenin. For finding this equation you can use any analysis such as nodal analysis has or mesh analysis. In this Thevenin's theorem, note one point, that is Thevenin's voltage always depends upon the source voltage. Thevenin's resistance is dependent upon the source voltage and current. Here, when network contains only dependent sources, effective resistance is R Thevenin. Thevenin's resistance will be negative when it has dependent sources, then only it is possible. When network contains at least one independent sources, then effective resistance will be not equal to the Thevenin's resistance. We will see some limitations of a Thevenin's theorem and Norton's theorem. Here we have two networks, source network N1 and load network N2. Now talking about the source network, there are some limitations to this source network. The source network should be linear, it should be bilateral, and it should be time invariant. It can have independent sources or dependent sources. Initial conditions may be available to this network. It should be compulsorily coupled with the load circuit, otherwise there is no meaning to this source circuit and it will be redundant. Now talking about the load circuit, it can be linear as well as non-linear, unilateral as well as bilateral, etc. It can have same as source network, dependent sources or independent sources. Second theorem, that is known as maximum power transfer theorem. It can be applied if the resistance whose power is maximized is variable. It is the best applications of a previous theorem, Thevenin's theorem. In this you have three cases. In the case 1, which you have a DC source with load is variable. For this, maximum power transfer to the load resistance RL is equals to R Thevenin, and we use the formula to find the maximum power as V Thevenin whole square is equal by 4 times R Thevenin. When load resistance is 0, maximum power will be infinite maximum. As load resistance increases to a certain value, the maximum power will be maximum. At R Thevenin it will be maximum power will be maximum. As R Thevenin increases and it falls to 0, maximum power also falls to 0. Efficiency of a maximum power transfer theorem is equals to 50%. Next we'll talk about the case 2. AC source with variable load impedance. In this you have voltage source, you have source impedance or Thevenin impedance as R Thevenin plus JX Thevenin. You have load impedance as RL plus JX. In this, inductor comes into the picture in this network. For this, when only load resistance is variable, maximum power transfer theorem, you will use the formula to find load resistance is RL is equals to under root R Thevenin square plus X Thevenin plus XL whole square. When only load reactance is variable, maximum power transfer to load is equals to XL is equals to minus negative term of X Thevenin. When overall load resistance and load reactance are variable, then maximum power transfer to the load, you will get RL is equals to R Thevenin, XL is equals to minus X Thevenin. Now coming to the case 3, you have an AC source with a source impedance R Thevenin plus JX Thevenin, and for load you have only resistance. So it is the AC source with variable load resistance when only load resistance is variable. To find for maximum power transfer to the load, to find out how much power is transferred to the load, you have to find RL by using the formula RL R Thevenin square plus X Thevenin square. So maximum power transfer theorem is one of the important concept in network analysis. From this you can expect a question in transco. From maximum power transfer theorem there is a node point, and that Pmax is equals to B Thevenin whole square by 4 times R Thevenin. This formula is valid only when network is resistive and RL is R Thevenin. If the network is not is not resistive, then you can use the formula Pmax is equals to Imax square into RL. Please keep in mind there is a special case in maximum power transfer theorem. See, in this circuit you have a Thevenin voltage, Thevenin resistance, and this is the load resistance and load sources. So voltage drop across a load will be half that of source voltage. With this information you can find the other parameters which we'll see in some other problems. Next we'll talk one of the important theorem, that is superposition theorem. From this also you can expect one question. Superposition theorem, it is applicable only for linear, bilateral and passive networks. When it is superposition theorem is applicable when a network consists of multiple sources containing voltage sources and current sources. If you want to find the equation by using the superposition theorem, and if you have voltage source and current source, first equation you should write by considering the voltage source and short circuiting the current source. Next current equation you should write by short open circuiting the voltage source and by using the current source. In AC circuits, use superposition theorem when sources have multiple frequencies, that I have explained before only by using one example. In superposition theorem, there are some limitations which must be kept in mind while calculating superposition theorem. Superposition theorem is not suitable to calculate the power calculations, and superposition theorem is not applicable for the diodes and BJTs. Superposition theorem is not suitable for transformers. Reciprocity theorem. In linear bilateral network, the ratio of excitation and response is always constant. It is applicable only for passive network. It is applicable for linear networks R, resistor, inductor, capacitor and transformer. These are the linear networks. In the presence of dependent source, network is active and non-reciprocal. In reciprocity theorem, we have three cases. See, consider this is at a two-port network. This is the port 1 and this is the port 2. In case 1, we will apply voltage sources at both the ports, that is port 1 and port 2. In case 2, current sources will be applied for port 1 and port 2. In case 3, voltage source at one port and current source at another port will be applied. In case 1, voltage source is applicable to port 1 and applied to port 2. Here current delivered by the voltage source is I1 and current delivered by the voltage source 2 is I2. This is the actual circuit which we have applied to the two port network. Here we will do two experiments. In experiment 1, voltage 1 is active and voltage 2 is short circuit. So when it is voltage source 1 is active and voltage source is short circuited, so it is 0. So in reciprocity theorem we will use output by input. Here output is the current coming from the I2 and the input is V1 where V2 is equals to 0. This is experiment 1. In experiment 2, second voltage source is active and first voltage source is short circuited. Here the input is V2 and output is I1. So I1 by output by input is equals to I1 by V2, V1 is equals to 0. In according to the reciprocity theorem, these two, experiment 1 and experiment 2, must be equal. So I2 by V1 is equals to I1 by V2. In case 2, we are applying two current sources at two ports. This is current I1 at port 1 and current I2 at port 2. This is the actual circuit. In first experiment, we will activate the first current source and we will deactivate the second current source. So it is open circuited. Here the output is V2 and the input is I1, keeping I2 as 0. In experiment 2, we will activate the second current source. We will deactivate the first current source. So this is output open circuited and this is input. So now equalize these two equations. So this equalize the two equations, you will get as V2 by I1 is equals to V1 by I2. In case 3, you will apply voltage source to port 1 and current source to port 2. Now by activating the first voltage source and deactivating the second current source, here the output will be V2 and input will be V1, keeping I2 as 0. This is the first experiment. In second experiment, you will activate the current source and short circuit the voltage source. This current source will act as input and this I1 will act as output. Here output by input will be I1 by I2. But in case 3, there is a small change. These two experiments will be negative for each other. So these three are the important cases which we will see in the reciprocity theorem, and this reciprocity theorem is applied only for initially relaxed systems. Please keep in mind this reciprocity theorem is applicable only for initially relaxed systems. Now we will say about the final theorem, that is nothing but the Telegraph theorem. In Telegraph theorem, it states that in any network, sum of power consumed by the various elements of a branches is always 0. It can be represented as summation from k equal to 1 to n pk is equals to summation from k equal to 1 bk ik is equals to 0. It has best application when network elements are unspecified. We will see some problems regarding today's topics. In this question, he has given 4 different types of graphs and he is asking to find out which is an active element. See, for such type of questions, we have to go smartly and answer the questions. See, here the slope is positive. In this graph also, slope is positive. In this graph also, slope is positive, which is increasing. In this graph, here slope is positive and this slope is negative. If the slope is positive, then we can blindly believe that it is a passive element. If the slope is negative, then it is an active element. Second question, this comes under the topic of inductor. Here the voltage and current waveforms are shown. We have to find out what is the element and what is the value of that element. See, in this the voltage source is constant and current is changing with respect to time. We know that inductor does not allow sudden change in current. So it is changing with respect to time and it is a ramp. Current is changing with respect to time and it is a ramp and it has a ramp. So here voltage is directly proportional to change in current. So we can conclude that if there is change in current with respect to time, it is an inductor. Here by finding slope, we will get a slope as 1 ampere per second. Here voltage is constant, that is 2 volts, and current is changing with respect to time 1. So di by dt is 1 and voltage is 2 volts. So from the formula V is equals to L into di by dt, we will get inductor as 2 Henry. Third question. In this question, a 100 ohms 1 watt resistor and 800 ohms 2 watt resistors, these both are connected in series. The maximum DC voltage that can be applied continuously to series circuit without exceeding the power limit of any of the series. In this question, he is saying that two resistors are connected in series and a voltage source is applied to this series circuit. We have to find out how much is that voltage source we have applied, so that the condition is the power limit should not exceed. For this, we have used the formula IRMS square into R. In first resistor, it has given 1 watt and 100 ohms. So P is equals to IRMS square into R. From that you will get I1 is 0.1 amperes. From second resistor you will get I2 as 0.05 amperes. If they are connected in series, the total current we will take it as minimum current of 0.1 and 0.05. We know by the Ohm's law V is equals to IR. Here we have got the current as minimum value 0.05 amperes, and here both resistors are connected in series, so we will use it as, we will add these two resistors, 800 plus 100, total 900 ohms. Here we have to find the applied voltage. V is equals to, the total current is 0.05 and the resistance is 900 ohms. From that we will get voltage as 45 volts. In this problem, I will tell you how to find out the, I will tell you the trick how to find out the IRMS value. See, this is a triangle and this is in the shape of square, right? Here you can find IRMS as, first we have to take total under root. So it is triangle in shape, so take amplitude by root 3 whole square into the time period out of total time period, plus next this is in the form of square, so it is of minus 10 by 1, we have took 1 because it is a square, into 2 by 4 because 4 minus 2 is 2. Okay, this is under whole under root. We'll get it as 100 by 3 into 1 by 2 plus 100, this is 2 ones are 2, 2 twos are 4, 100 by 2. Here you will get as under root 50 by 3 plus 50. You will get it as under root 150 plus 50, 200 by 3. He is asking about the average power. Average power is nothing but IRMS square into R, which is equals to 200 by 3 and resistance value is of 2. So 400 by 3. You will get it as 133.3 watts. In this question, I'll tell you how to find out the RMS value. See, first consider this as A, this as B, and this is 8 amperes. Okay. Now IRMS you can find out by under root whole under root 2 by 1 whole square into time period by total time period plus 8 by root 3 whole square into function time period by total time period plus 2 times the magnitude of A part into half into base into height of the B part, which is triangle, that is nothing but half into base into height of total time period. By this you will get under root 4 by 2 plus 64 by 6 plus this both will be cancelled and 8. So you will get it as 62 by 3 amperes. This is the main thing you have to keep in mind. 2 times amplitude of square component and half into base into height area of a triangle component. Next question, this will come under the topic of capacitance, energy stored in the capacitance. Here the waveform of current is shown in the figure. We have to find the energy stored in capacitor for 0 to 2 seconds and 2 to 3 seconds. First we'll think about 0 to 2 seconds. Here initial voltage is given as 2 volts, Q is equals to CV. Here V is 2 and C is 4 microfarads. You will get it as 8 microcoulombs. We know that energy is equals to half CV square. Half Q is equals to CV. We can write as Q square by 2C. So initially energy stored in the capacitor is 8 microjoules. Now in the next stage, Q2 is initial charge plus half into base into height. You will get as second charge 10 microcoulombs. Second energy stored, so you will use the same formula Q square by 2C. You will get it as 12.5 microjoules. By subtracting the second energy and first energy, you will get as 4.5 microjoules. Here secondary charge you got as 10 microcoulombs. Now add this secondary charge to this, you will get as 12 microcoulombs, and energy stored is third energy stored minus second energy stored. You will get it as 5.5 microjoules. In this, the current waveform is shown and this current is passing through the capacitor. He is asking to find the charge acquired by the capacitor till 6 microseconds. Till this time he is asking. So to find out this, we will use the formula of charge. Q is equals to integration of I of t into dt. Integration is nothing but area. This is area 1, area 2, and this is area 3, and this is area 4. Area 1, will it is in the form of triangle. We'll write it as half into base is 3 and height is 5. Area 2, half in, this is also in form of triangle, half into base is 1 and height is 2. Area 3, this is also half into base into height, you will get 4. Area 4, which is in the form of square, so 3 into 3, 9. By adding those all values, area 1 plus area 2 plus area 3 plus area 4, we will get the charge acquired by the capacitor till 6 microseconds, that is 19 microcoulombs. This problem is related to the current division rule. In this, it has a source current of 16 amperes. He have mentioned it as I1, I2, I3, I4. He is asking to find out the value of I2, which is in the 200 ohms. So for I2, here the 4 resistors are connected in parallel. So I2 is equals to source current I1 into reciprocal of this resistance by reciprocal of all resistance. By doing like that, we'll get the value of 1.2 ohms, which is a basic question. In this question, the waveform of current passing through an inductor of resistance 1 ohms and inductance 2 Henry. He is asking to find the energy which is absorbed by the inductor for first 4 seconds. Like these problems, first we have to find out the energy stored in the inductor by using the formula half Li square. Next we have to find the energy dissipated by the resistor, which is equals to I square R. By finding these two values, we can find out the energy absorbed by an inductor. First we have find out energy stored in the inductor by using the formula half Li square. In this, I took inductor L as common, and till 4 seconds I square of 4 minus I of 0. For 4 seconds the amplitude is 6 amperes, and for 0 seconds it is 0. So by calculating you will get it as 36 joules. Here I have find out the current slope, which is equals to y2 minus y1 by x2 minus x1. Here 6 by 2 with respect to time, this is 3t. Next we will find the power in the resistor. Energy dissipated in the resistor with respect to time, we will integrate 0 to 2 seconds of 3t square into 1 into dt, and 2 to 4 seconds of 6 square amplitude square into 1 into dt. By this you will get the value as 96 joules. So total energy absorbed by the inductor is equals to energy stored by the inductor and energy dissipated by the resistor, which will be absorbed by the inductor. This question comes under the Thevenin theorem. In this circuit, he is asking to find the current I, which is shown here. In this circuit, he has divided into two parts. For this part, he had found the current across 7 ohms and voltage across 7 ohms and Thevenin resistance across 7 ohms. See, he had used the current division rule. The current flowing in the 7 ohms is equals to 5 ohms into opposite resistance by total resistance. Total resistance is 3 plus 7 plus 4 is equals to 11. Then voltage across 7 ohms. he has used voltage transformer. 5 3s are 15. Okay, 15 into opposite resistance by total resistance is 14 ohms. R Thevenin, this will be open circuited. 4 plus 3 is 7. 7 parallel with 7 you will get as 3.5 ohms. Now I had replaced this total circuit here. 7.5 volts as V Thevenin. R Thevenin is 3.5 ohms, and he has done the so, source transformation. 17 3s are 51 Vx, 17 ohms, in series with 17 ohms, 2 ohms, and he has done the source transformation here also, 9 volts 9 ohms. By doing those equations you will get current as 21.276 milliamperes. In this question, for the value of R greater than 1 such that it absorbs 5 watts of power, he is asking to find the value of R. This is dependent source, independent source. Here the current flowing in this circuit is Vx by 2. He has written that Vx by 2 is equals to V1 by 2 plus R. From this you will get Vx. Here he have done nodal analysis. V1 minus Vx by 4, V1 minus 20 by 4, V1 Vx by 2. By solving those equations you will get the value as this much. In this he have took 2v1 common and 2 and 20 cut by 10 times, so you will get the v1 value as 10 into 2 plus r by 3 plus r. Next he has used IRMS square into R formula. In this resistance the current flowing is Vx by 2, so he took Vx by 2 whole square into R is equals to 5 watts. Here you have got Vx value as 2v1 by 2 plus R. Here 2 get cancelled. V1 by 2 plus R into R is equals to 5. By substituting V1 value you will get R value as 13.32 ohms. This question is related to the superposition theorem. In this circuit you have two independent sources. One is voltage source and another one is current source. Superposition tells us to use the any one source at a time and short circuit the voltage source, open circuit the current source. So first we have took here voltage source as energizing circuit and we have opened the current source. So we'll get a circuit like this. In this, from this the current is flowing like this. I1 is equals to voltage source by total impedance. Here plus J4 and minus J4 get cancelled, you will get value of 6. You will get 2 by 3 amperes, which is I1. Next we will consider only current source and we will short circuit the voltage source. Here the current 4 at an angle of 90 degrees is flowing like this. We have to find the current in 3 minus J4. Here we will use the current division rule. I2 is equals to 4 at an angle of 90 degrees plus 90, we can use it as J4 into opposite impedance 3 plus J4 by total impedance. You will get the value as minus 8 by 3 plus J2. Now we have to equate or sum these two currents I1 plus I2. From that you will get as minus 2 plus J2. We have to take the magnitude as 2 square plus 2 square at an angle of 180 minus tan inverse of 2 by 2. Why? Because here real part is negative and imaginary part is positive. So you will get as 2 root 2 at an angle of 135. In these four quadrants I will tell you the value of theta. Theta will be tan inverse B by A in first quadrant. Here theta 2 will be 180 minus tan inverse B by A. Here theta 3 will be minus 180 plus tan inverse B by A. Here theta 4 will be minus tan inverse B by A. Here real part is positive and imaginary part is positive. Here real part is negative and imaginary part is positive. Here real part is negative and imaginary part is also negative. Here real part is positive and imaginary part is negative. This question is related to the Thevenin's theorem. In this question, he is asking to find out the open circuit voltage and Thevenin resistance. Here, V2, this current is passing through 20 kilo ohms and the V2 is minus 50 I1 because current is entering the negative terminal into 20 kilo ohms. You will get as minus 1000 kilo ohms into I1. Here he has used the KVL. 2 millivolts is equals to 2000 I1 plus V2 by 5000. Here you have used the V2 value, you will get as 1800 I1. I1 is equals to 2 millivolts by 1800. Here V2 is equals to minus 1000 kilo ohms into I1. I1 value you have substituted, you will get it as minus 10 by 9 volts, which is minus 1.11 volt. Next, to find RThevenin, we have to compute ISC. For ISC, short circuit the open circuit voltage source. So total current will be passing through this ISC. This current is opposite to ISC. You will get it as minus 50 I1. V2 is 0. As V2 is 0, this will become useless. I1 will be 2 milliohms. This will be short circuited as it is 0. I1 is equals to 2 millivolts by 2 kilo ohms. You will get as my 1 microamperes. Here ISC is 50 I1, which is 50 into 1 microamperes, that is minus 50 microamperes. RThevenin formula is VOC by ISC. By substituting the previous values, you will get answer as 22.2 kilo ohms. This question is related to the supernode concept. See, between these two nodes you have a one source dependent source voltage, so supernode concept is applicable. In this, the current is entering into the node 3 milliamperes is equals to current Vx by 2 minus 4Vx by 40, and here minus 4Vx by 5. By calculating this, you will get the value I as 6 milliamperes. In this question, he is asking to find the current I. This is VAB. By voltage division rule, we will get the value of VA 5 into 1 by 2, 2.5. We will get the value of B 4 VAB into 1 by 4, that is equals to VAB. VAB is equals to VA minus VB, where VA is 2.5 minus VB is VAB is equals to VAB. VAB value will get as 1.25. I is equals to 4 VAB by 4, which is equals to VAB, that is 1.25 amperes. In this question comes under superposition theorem. In this question, the linear circuit is given: voltage source V1, current source I1, current source I2, and current source I3. Here I1 is, if I1 is 3 amperes, then output voltage is 16 volts. If I1 is 1 ampere, output voltage is 8 volts. If I1 is 0.5 amperes, then what will be the output voltage? For 16 volts, it is 3 amperes. Means for 8 volts, it will be 1 ampere. For 0.5 amperes, how many volts? For this we have to write the equation. Vs is equals to 16a plus 3b. Vs is equals to 8a plus b. From these both equations you will get the value of a and b. From a and b values you will get the value of Vs. If Vs is minus 4 volts, we have to find output voltage into output current. He has given us 0.5 amperes into 4. So while calculating this, we will get the values as 6 volts. Output voltage as 6 volts. This is the question of IES. It comes under the concept of capacitor. Question is, an uncharged capacitor of 0.01 farad is charged first by a current of 2 milliamperes for 30 seconds and then by a current of 4 milliamperes for 30 seconds. He is asking to find the final voltage in it. Here we use charge conservation top. It is an open circuit, so charge remains constant. Initial charge is equals to final charge. Initial charge is C, initial voltage is V, and final charge is 2 milliamperes for 30 seconds plus 4 milliamperes for 30 seconds. This into milli. So 60 plus 120 you will get as 128 milli coulombs. Here he is asking to find out the final voltage. So it is 180 into 10 power minus 3 divided by capacitance value is 0.01 farad. So 180 into 100 divided by 1000, 3 zeros. Finally you will get it as 18 volts. This question was regarding about the ideal voltage source. In this statement, its output voltage remains absolutely constant whatever the change in load current. It possesses zero internal resistance so that internal voltage drop is zero. Output voltage provided by the source would remain constant irrespective of amount of current drawn from it. Output voltage provided by source varies with amount of current drawn from it. From these four statements, first three statements are correct. This is because for this ideal voltage source, here voltage remains of constant irrespective of the current drawn from it. An ideal voltage source has zero internal resistance, which is the second statement, that is correct. Output voltage is equal to the source voltage, which remains constant irrespective of current drawn from it. So first three options are right. This question was asked in IES 2018. This comes under the topic of inductor. Here a pulse of 10 volts in magnitude and 2 seconds in duration is applied to the terminals of a lossless inductor of 1 Henry. He is asking to find the current through the inductor. Here voltage magnitude is 10 volts and time duration is 2 seconds. He is asking to find out the current through the inductor. Current is equals to 1 by L integration of V of t into dt. Here inductor value is given in the question as 1 and integration of from 0 to 2 seconds V is 10 into dt. Here you will get I is equals to 10 into t from 0 to 2. When we substitute the values, 10 into 2 is equals to 20 amperes. This is the value of current. In this question, he has given the voltage waveform, a triangular voltage waveform. This voltage waveform is applied to the terminals of a capacitor of 0.5 farads. He is asking to find out the corresponding current wave. Now consider from 0 to 2 seconds, there is a slope m1. You will get as minus 10 by 2 minus 0. You will get as minus 10. Voltage you can write it as minus 10t plus C1. Similarly, from 2 to 4 seconds, you will get M2 as minus 10 by 2. You will get as 10. So you can write VT as 10t minus C2. Similarly, from 4 to 6 seconds, you will get M3 as minus 10. Voltage equation you can write it as minus 10t plus C3. We know I is equals to C into dV by dt. In this equation, current is equals to C is half, which is given in question, d by dt of minus 10t. You will get it as minus 5 amps. Similarly, in this, I is equals to 1 by 2 into d by dt of 10t. You will get it as 5 amps. Similarly, in this, I is equals to minus 5 amps. So by drawing the waveform from 0 to 2, 2 to 4 and 4 to 6, here we got from 0 to 4 current as minus 5 amp. This is 5 and this is minus 5. You will get it as 0 to 2 minus 5, and next 2 to 4 you will get it as 5 amperes, and 4 to 6 you will get it as 5 amperes. This is the current waveform which is given in the option B. This question comes under the topic of inductor capacitor. Here he has given the voltage waveform and he has given the current waveform. He is asking to find the nature and value of an element. Before solving this problem, you have to know some basic terms. There are some different types of signals: impulse signal, unit step signal, ramp signal, and parabolic signal. If we will do integration of impulse, you will get unit step. Integration of unit step, you will get ramp. Integration of ramp, you will get parabolic. And if you do differentiation of parabolic, you will get ramp, and differentiation of ramp, you will get unit step. Differentiation of unit step, you will get impulse. Here current waveform is parabolic in nature and voltage waveform is ramp in nature. So here current is parabolic, means integration of ramp ramp is voltage signal. So integration of voltage signal will give you a parabolic signal. This is the equation which we will use to solve this problem. Here he is asking from 0 to 2 seconds voltage is 10t into dt. So you will get as I is equals to 10 by L into t square by 2 for 2 to 0. You will get it as 5 by L into t square from 2 to 0. Current at 2 seconds is 8 amperes. So substitute those values. 8 amperes is equals to 5 by L into 4. So inductor is equals to 20 by 8. 8 2s are 16, 2.5 Henry. So from these options, option B is right answer. You will get an element of inductor 2.5 Henry. Similar question which was asked in ESE 2017. Here the current waveform is ramp in nature and the voltage waveform is unit step. Here current is ramp and voltage is step. So you want to get step signal from ramp signal. V is equals to V is step from ramp signal. Here you will use the formula V is equals to L into di by dt, where current is ramp and voltage is step. To get step signal, you will differentiate the ramp signal. So here voltage is 1 and inductor differentiation of current is 1 and voltage value is of 2. So you will get inductor of 2 Henry. So option B is right. In this question, a wire of resistance 5 ohms is further drawn or stretched that its diameter becomes 1 by 5th of its original value. He is asking to find the resistance if volume remains constant. In this question, he had told that volume remains constant. V1 is equals to V2. So volume is pi r square h1 is equals to pi r2 square h2. Pi cancel. R1 square by R2 square is equals to H2 by H1. When diameter becomes 1 by 5th of radius, radius also becomes 1 by 5th. So it will become 25 H1 is equals to H2. Length will become 25 times of H1. We know formula of a resistance R is equals to rho L by A. R2 is equals to length becomes 25 times and area of cross section, that is pi r square. So Area is R1 by 2, R1 by 5 whole square, which is 1 by 5 whole square into R1. You will get it as 25 into 25, 625 into R1, which is 5 ohms, that is 3125. There is uh, one shortcut to find this formula. Resistance is always inversely proportional to diameter power 4 or inversely proportional to radius square. Here d2 is 1 by 5 of d1, so r1 by r2 is equals to d2 by d1 whole power 4. So r1 is 5 ohms and r2 is this much, and d2 diameter you will get it as 1 by 5 whole power 4. So r2 is 625 into 5, which is 3125. This is the shortcut.